Hi. So in this three-dimensional static equilibrium problem, we're asked to find the axial force in member AC on this little boom OAB that has two cable-like members supporting the little boom, and then we've got the 4 kilonewton applied load down here that is acting downwards -4 in the K direction. That's the Z direction. Note, X is horizontal, Y is horizontal, but Z is now our vertical direction. All right, so in this kind of three-dimensional problem where we only want one force, we ought to be thinking about being clever in how we look at the 3D equations of equilibrium, rather than setting up a generic system of forces, sum of forces or sum of moments about a point, and doing it that way. Since we only want one thing, the three-dimensional equivalent of what we do in 2D is to take a moment of a vector about an axis and use that as our way to go about simplifying the mathematical manipulation of the problem. So note that we've got here our force AC that we're interested in, and we're not really interested in the force BD, and we're not interested in the three reactions that we get at this little pin support out here at point O. So the convenient thing to do is to find a axis that as many of these forces we don't care about are going to cross. So this force here and these three reactions would all go through a line that passes through OD. So that's what we want to do, is some moments about that axis, and that will make life a lot easier for us in terms of the overall manipulations. So with that in mind, we're going to need to know the orientation of this force that's in member AC. That means let's go find a unit vector along A to C. We'll do that by figuring out the position vector from A to C. A is in the vertical plane formed here in the YZ plane, so AC marches forward 0.4 meters I. It's going to go backwards J. So let's get an orientation in here. Notice we can draw a 30-degree right triangle on the vertical plane, and so since OA, the hypotenuse, is 0.9 meters, then that makes then our movement in the y direction 0.9 times cosine of 30 degrees, and then we're going to come up by a sine of 30 degrees times 0.9. Sine of 30 is 1/2, so that will be 0.45. Okay, now that's just the position vector from A to C. We want the unit vector, so we need to take the square root of the sum of the squares of each of those components. When you work this out, you'll get about 0.779, and then we have the 0.45 squared as well, and that will give us a position vector A to C that is 0.406 I minus 0.791 J plus 0.457 K, right, at least to a rounding level. Now the other thing we're going to need is the unit vector that goes along OD, and that one then is going to be, we're going to march backwards minus 0.4 I. We're going to march forward in the Y direction, 0.8 J. We're entirely in the horizontal plane, so there is no K component to work with, so we'll have 0.4 squared plus 0.8 squared and square root thereof, which turns out to be the square root of 0.8, interestingly enough. And we will have then a minus 0.447 I plus 0.894 J approximately that we're working with. Should have done that in red to help highlight that, so I'll just underline it to help draw it out. Those are the two unit vectors that we want. And now it's just a matter of summing moments about that axis OD, which when we sum moments, that's going to turn out to be a scalar here. Now that's just really crummy symbiology. What we really want to do is find the scalar moment about the axis OD, and that's going to be the sum of our R cross F and then dot our unit vector, and we're going to set that equal to the scalar value of 0, right? Because a dot product is a scalar, right? So let's do the let's see, which one do we want to do first? Let's do the work associated with our force B, right? Its position vector anywhere from along this axis down to here works fine. Notice anywhere to the line of action of the force works fine. So if we go on that part, then we'll have 1.2 cosine 30 degrees J as the position vector for this force here, which is minus 4k, not as a k in kilonewton, but k is the unit vector. And then we're going to dot that with the unit vector along our axis, u dot OD. I'm going to just leave it like that for a moment. And then along AC, or for that force there, note that we can choose any position vector we want that goes to the line of action. So why not choose the easy one that goes from O to C? And that position vector then is just 0.4I, and we'll cross that with our unknown magnitude force of the force FAC. That's a scalar magnitude times the unit vector AC. And then of course we need to dot that with our axis vector. And so that sort of begins to set it up here. Trying to do this in little tiny pieces and stages to make it a little bit easier to work along the way. We'll get for this first one a minus 4.157, that's the numbers, and then we got J cross K. Remember our little circle here for positive. I cross J is a K, and J cross K is a positive I. And we'll dot that with UOD, which is minus 0.447I plus 0.894J. Plus, we'll have that magnitude FAC. Pull that out. We've got the 0.4I cross our UAC. That's 0.406I minus 0.791J plus 0.57K, and that's getting already pretty long, so I'm just going to leave this as dot UOD for the moment. Get the pun here? Leave that for the moment. Alright, so now we got, in this very long solution here, minus 0.4157 I dot something I and something J. Well, the I dot J is a 0. You only dot yourself, and so now we'll have, when we work that out, a minus this times a minus that, and the I dot I gives us a 1. That will give us about 1.859. Depending on how many digits you keep, you might get an 1858 instead of a 1859. Plus FAC times, we've got I crossing itself, and remember you never want to cross yourself, so that you get nothing when you cross yourself. So I cross I is a nothing, it's a 0. We get an I cross a J, that's a positive K, so 0.4 times a minus 0.791, then think it's 0.3164, but let's double check that here. 0.406. Oops, sorry. 0.4 times 0.791 is 0.3164. That's minus 0.316. I cross J would be a K. And then I cross K is a minus J. And 0.4 times 0.457, that's 0.1828, or about 0.183. And then that's going to get dotted by the UOD, which was minus 0.447 I plus 0.894 J. Right, we're still trucking along. 1.859 plus FAC. Now notice, we're going to do K dot I, that's nothing. K dot J, nothing. We've got a J dot I, nothing. And so all we're left with is the J dot J, or 0.183 times the 0.894. That's 0.163. And that would be a negative value. And that's all being set equal to 0. And when you solve for that, then we find out that FAC is equal to about 11.6 kilonewtons. Now, a couple words about that number. You might get 11.3, you might get 11.4. A lot depends upon the how many digits you kept all along the way. Note, how did I know the units? Well, because FAC from the very beginning, that was in kilonewtons. UAC is in meters. All the position stuff, sorry, that's a unit vector. That's in meters. So we have kilonewton meters going on all along in here. That was in kilonewtons. This is in meters. And so when you are paid very close attention, you get then 11.6 kilonewtons.